This is Calculus 2 video lecture number 2 on trigonometric integrals. So the basic way to conquer this topic is to learn the cases and then recognize them when they appear and apply the appropriate strategy. So the first case we're going to look at is how to evaluate the integral of sine raised to the nth power of x times cosine raised to the nth power of x dx. So basically you have a product of powers of sines and cosines. And the first case we're going to look at is if n is equal to 2k plus 1. So if the exponent on cosine is odd. All right, how do you deal with that? And then we're assuming in this case the exponent on sine could be even or odd. Well, what you do is you factor out or you separate one of the powers of cosine of x. And the goal is for that one little cosine of x to get absorbed with the dx when you make a u substitution. And the cool thing is now that you have cosine raised to the 2k, right, of x, that means that's going to be an even exponent. So I can rewrite it as cosine squared raised to the k, cosine squared of x, and then replace cosine squared with sine squared of x. So you're going to make a u substitution, let u equal sine of x, and then that means du is going to be cosine x dx. And there he is waiting for us, that one little lonesome cosine that we plucked off. And from there, then it becomes a really straightforward integral to evaluate because you're just going to have a nice little polynomial. So you're going to have, remember, sine of x is u, so you're going to have u to the m. And then that 1 minus sine squared is going to be 1 minus u squared raised to the k. And then cosine x dx, remember that's our du. And then etc. From there, you just multiply everything out, and anti-differentiating is usually pretty straightforward. So let's look at an example. Sometimes it's hard to exactly visualize how this is going to work until you get into it. So here we have integral of sine raised to the 6th of x and cosine cubed x dx. All right, so whichever trig function is odd, in this case we're focusing on the power of cosine being odd, you're going to pluck off or factor out one of the factors of cosine, separate it. So I'm going to leave sine to the 6th x alone, and then now I have cosine squared x times cosine x dx. Okay, so all three are still accounted for. Now here's what you need to think to yourself. This is what I want to get absorbed when I make my u substitution. So I want this to be du, basically. So just think backwards, right? If I want cosine x dx to be du, then that means u would have had to have been sine x, correct? Good. Then everything works out. So then du would be cosine x dx. And then you look back at your integrand and you go, all right, can I switch everything so that it's in terms of u? No problem here. That would be u to the 6th. But wait a minute. Cosine squared x, I have to rewrite that in terms of sine so I can make my u substitution. Well, we got our Pythagorean identities. So I'm going to have sine to the 6th x. I'm going to replace that cosine squared with 1 minus sine squared x. And then leave cosine x dx because that's going to get absorbed as du. So there's where my cosine squared x went, and then leave the sine to the 6th x there. Don't do part of the substitution and then leave other parts still in terms of the original variable. Do you get what I'm saying? Don't have u's and x's mixed at the same time. That's not proper. So now we can make our u substitution. So sine to the 6th x, that's going to be u to the 6th. 1 minus sine squared, that's 1 minus u squared. And then cosine x dx is du. Beautiful. Now we're home free, right? All you need to do is distribute this bad boy. So we have integral u to the 6th minus u to the 8th du. Let's anti-differentiate. So I'm going to have 1/7 u to the 7th minus 1/9 u to the 9th plus c. And, we're not done. I have to rewrite everything in terms of the original variable. So remember, u was equal to sine x. So I'm going to come back, replace all these u's with sine x. So this is going to be 1/7 sine to the 7th of x minus 1/9 sine raised to the 9th of x plus c. And we're done. Very nice. How was that? Okay, let's look at another example here. Same case, the power of cosine is odd. Notice in this integral, we don't have any powers of sine of x, no problem. And this is a definite integral. So this time I have limits of integration. So we'll have to deal with that. Same idea though, you pluck off one of the factors so that that can get absorbed in the du, in the u substitution. So we have 0 to pi halves, and then I'll be left with cosine to the 4th x times cosine of x dx. All right, so remember, I want this to be absorbed as du, so think backwards. What would u have to be? Well, u would need to be sine x, and then du would be cosine x dx. Wonderful. However, I currently have cosine of x raised to the 4th, and remember, I need u to be sine x, so I got to rewrite that in terms of sine. Well, how am I going to do that? Cosine to the 4th x is cosine squared squared. So this is going to be 1 minus sine squared x squared. Still from 0 to pi halves, cosine x dx. Okay, now take a look. Am I in a good shape to make that u substitution now? Absolutely. I just have to figure out first what my new limits of integration are going to be. Okay, so let's do that before we get rolling. So I'm going to substitute in that lower limit, 0. So u of 0, that's sine of 0, that's going to be 0. And then upper limit is pi halves, so u of pi halves, that's going to be sine of pi halves, which is 1. All right, so let's write out what our new integral is. Everything in terms of u. So my new limits are going to go from 0 to 1. 1 minus sine squared x, I'm going to replace that with 1 minus u squared. That's all squared. And then cosine x dx is du. All right, what a nice clean little integral. So now all we have to do is multiply this out. So we have integral from 0 to 1, 1 minus 2u squared plus u to the 4th du. Let's go ahead and integrate term by term. So I'll have u minus 2/3 u cubed plus 1/5 u to the 5th. Evaluate that from 0 to 1. Love it. Looks nice. All right, time to plug in those limits of integration. So plugging in the upper limit of 1, I'll have 1 minus 2/3 plus 1/5. And then always make sure you plug in 0. Don't take it for granted that it's always going to come out to be 0. In this case, it is. But always stop and think about it. Sometimes it'll sneak up on you. Okay, our common denominator here is going to be 15. So this is 15 minus 10 plus 3. All over 15, so 5 plus 3, we have 8/15 as our final answer. Very good. Do we feel like we have the hang of that first case? Wonderful. Now it's time to move on to case 2. So case 2 now says m is equal to 2k plus 1, which means that it's odd. Then you're going to rewrite it as follows. So the only thing that's different with case 2 is that now the power on sine is odd. And so in this case, I can write it as 2k plus 1. You're going to pluck off one of the factors of sine. So now you have sine to the 2k of x, which means it's even. So I can write it as sine squared to the x. And then you guessed it, this time you want sine of x dx to get absorbed as du, which means you're going to let u equal cosine x for this case. But you do pick up an extra negative. So du would be negative sine x dx. And so you just have to remember to add that negative du in when you replace sine of x dx. Okay, and so your new integral would have the following form. You'll have that negative integral 1 minus, remember cosine x is going to be u, so we have u squared. This is all raised to the k, whatever k may be for that particular problem. Then you would have u to the n, that's cosine to the nth of x, and then there's your du. And then you just multiply it all out like we did before and anti-differentiate. Okay, so here let's look at an example. Number 3, evaluate the following integral. This one is from 0 to pi halves, so we have a definite integral this time, of sine raised to the 9th of x times cosine to the 6th of x dx. Okay, so what I'm going to do to start off is pluck off one of those factors of sine. So I'm going to write this as 0 to pi halves. Sine, now it's to the 8th of x. Cosine to the 6th of x, and then you have sine of x dx. All right, so remember, I want that to get absorbed, that sine of x dx, when I make my u substitution. So then what would u have to be? Just think backwards. That means I would have to let u be cosine of x, and then du would be negative sine of x dx. A useful phrase to remember this process or this method is think of pulling the odd man out. Right? So if the exponent on sine is odd, you're going to pull one of them out to get absorbed in the du. And in the first case, when the exponent on cosine was odd, you pulled one of those out so that that could get absorbed in du. If they're both odd, guess what? You could do either one. All right, now let's see here. Are we ready to make our u substitution if u is equal to cosine of x? Well, this would be fine. This would be u to the 6th. Sine of x dx, that would be negative du. But wait a minute, we've got this sine raised to the 8th of x. That's no good. So what I have to do is remember that sine squared x raised to the 4th. So I'm going to replace sine squared x with 1 minus cosine squared x raised to the 4th. Okay? So get it all set up before you start trying to change everything in terms of u. So you do it nice and clean and you don't make any silly mistakes. All right, looks like we're ready to roll. The only thing I have to do before we make our change of variables is figure out my new limits of integration. So let's plug in lower limit of 0. So u of 0, that's going to be cosine of 0, which is 1. And then pi halves, u of pi halves, that's cosine pi halves, which is 0. Love it. All right, time to switch things up. So I'm going to have integral. New lower limit is 1. New upper limit is 0. 1 minus cosine squared is going to become 1 minus u squared. Okay, let's matchy-matchy with the color so you see what's going on. Raised to the 4th. Cosine raised to the 6th of x. Remember, u is cosine of x, so this is going to be u raised to the 6th. And then sine of x dx, that's going to be negative du. I'm going to put the negative out front. Okay, let's keep track of what happened here. Sine of x dx is negative du. Okay, this problem is just crying out for us to flip those limits of integration and get rid of the negative. Don't you agree? So 0 to 1, 1 minus u squared to the 4th times u to the 6th du. And then you might sit there for a second and think, oh my goodness, do I really have to multiply that out? Could I get away with a u sub? Like another substitution? No, you cannot. So yeah, you have to multiply it out. Or if you remember how to use Pascal's triangle in the binomial theorem, that might save you some steps. But in case you don't, I'll just show you how to multiply it out. So here we go. 1 minus u squared to the 4th. Well, that's 1 minus u squared squared. Squared. So that's going to give me 1 minus 2u squared plus u to the 4th squared. So one more time. Okay, and then you just multiply it out and enjoy the process. So here we go. I'm going to distribute the 1. So we have 1 minus 2u squared plus u to the 4th. Then distributing the negative 2u squared, negative 2u squared plus 4u to the 4th minus 2u to the 6th. Stack it this way so your like terms are already all near each other, right? Plus, and then now I'm going to distribute the u to the 4th. So I have u to the 4th minus 2u to the 6th plus u to the 8th. And then cleaning everything up, I'll just put it all over here. So I have 0 to 1. This is going to give me 1 minus 4u squared plus 6u to the 4th minus 4u to the 6th plus u to the 8th times u to the 6th du. Whew! All right, we're not quite there yet. You still have to distribute this u to the 6th to everybody. Yes. All right, so we have integral 0 to 1, u to the 6th minus 4u to the 8th plus 6u to the 10th minus 4u to the 12th plus u to the 14th du. And now you can anti-differentiate, whoo, at long last. So here we have 1/7 u to the 7th minus 4/9 u to the 9th plus 6/11 u to the 11th minus 4/13 u to the 13th plus 1/15 u to the 15th. Thank goodness it's just from 0 to 1 and not some other wacko number. Okay, so let's plug in those limits of integration. So we're going to have 1/7 minus 4/9 plus 6/11 minus 4/13 plus 1/15 minus 0. You have to figure out what the least common denominator is. It's going to be, let's see, 7. I've got 9, so that's 3 squared. I need 11. Wow, these are almost all co-prime. 13. 15, that's 5 times 3. I've already got a 3, so just add a 5 in there. So this is going to be 45,045. And then I'll let you play around with that. Hopefully you can do fractions if you're in Calculus 2. If not, get it together, and you should end up with 128 over 45,045. Beautiful. All right, are you ready for the next case? I hope so. So, this case is if m is equal to 2k and n is equal to 2p, meaning both of these exponents are even, ooh, then what do? You're going to rewrite them as sine squared raised to some power and then cosine squared raised to some power. Then it's time to use your half angle identities. So if you haven't put these to memory yet, now is the time, because you're going to integrate sine squared x and cosine squared x so much when you're in Calculus 2, Calculus 3, it doesn't go away. So burn these in your brain. Sine squared x is equal to 1/2 times 1 minus cosine of 2x. And then the only difference for cosine squared x is it's 1 plus cosine of 2x. So they both have cosine 2x in them. I just think the one for cosine squared is positive because it's the same. So it's in agreement, it's positive. The other one's the opposite for sine. And then you could also use the double angle identity for certain integrals. It depends on the setup. If you don't remember where this comes from, hopefully you remember that sine of 2x is equal to 2 sine x cosine x, right? And then basically if I divide by 2, so I isolate sine x cosine x, that's where I get this rearranged version of the double angle identity, which can be helpful sometimes, okay? Because then you can get rid of that product of sine x cosine x, and then you just have sine 2x, the constant's not a problem, and that 1/2 is not a problem either when we anti-differentiate, okay? Good. So let's look at some examples here. This is by far the trickiest case when they're both even, okay? So don't get disheartened. Here we go. Example 4, evaluate the integral. I have x times cosine squared x. And you might be like, wait a minute, you didn't tell me about having x times an even power of sine or cosine. Well, we're doing a combo problem right now. We're going to do by parts, and within that by parts, we're going to have to integrate cosine squared x, okay? So integration by parts was video lecture number 1. I'll link it right here in the upper corner in case you need to watch that before you get going here. All right, so to set up by parts, remember we pick one part of our integral to be u, the other part to be dv. So I'm going to let u equal x, and then dv is going to be cosine squared x dx. So that means du is dx, and then v is going to be whatever the antiderivative of cosine squared x dx is. So whatever the antiderivative of, and then we just went over those half angle identities to use. Do you remember it? It's going to be 1/2 times 1 plus cosine of 2x dx. So let's see, we can do this. I'm going to have 1/2 antiderivative of 1 is just going to be an x. And then plus, I'm going to divide by 2 when I antidifferentiate here, so it would be a 1/2 sine 2x, but remember I have that 1/2 sitting out front, so it's a 1/4 sine 2x. All right, good. So now we're ready to roll with by parts. So we have u times v. So we have u times v. That comes outside the integral. So this is going to be 1/2 x squared plus 1/4 x sine 2x minus integral of v du. So that was this product, u times v minus v du. That's what we integrate. So that's going to be 1/2 x plus 1/4 sine 2x dx. Okay, here's the green coming in at you. There we go. All right, can we anti-differentiate that? Absolutely. We don't have to do anything fancy schmancy. Let's just go. So I've got 1/2 x squared, remember that we don't integrate, plus 1/4 x sine 2x minus, so antiderivative of 1/2 x, that's going to be 1/4 x squared. And then antiderivative of sine 2x, it's going to be a negative 1/2 cosine 2x. But then look, I already have another negative, so that'll make it positive. And then since I have this 1/4, it'll be a 1/8 cosine 2x plus c. Whew! Should we box it? Are we done? No way, look, we can combine some like terms. Check that out. All right, so now I have 1/4 x squared plus 1/4 x sine 2x plus 1/8 cosine 2x plus c. Now you can box it with pride. That was well done. That's a nice problem too, because it'll test that you know how to integrate using by parts and with this trig identity. Okay. Next example for this case, I have integral from 0 to pi of sine squared x cosine to the 4th x dx. Okay. So in this case, I'm going to replace both of them with the appropriate half angle identities. So we have 0 to pi. Remember, sine squared is 1/2 times 1 minus cosine 2x. That's where that one went. And then since it's cosine to the 4th, I'm going to square the identity. So this is going to be 1/2 1 plus cosine 2x and then square it dx. You see that? Because it was raised to the 4th. Okay, so how do you multiply this out and not lose your mind? Well, first thing, you take the constants out of there. So this is 1/2, and then this 1/2 is squared, which means I've got a 1/8 sitting out there. Okay, love it. Then we've got 1 minus cosine 2x, and then I have 1 plus cosine 2x squared. So that means I've got 2 of them, right? Now there's a slick way of multiplying this out so you don't make more work for yourself. These are conjugates, which means if I multiply them out, I'm going to get a difference of squares. So multiply those 2 factors out first. So we have 1/8, 0 to pi. I'm going to have 1 minus cosine squared 2x now, and then 1 plus cosine 2x dx. Good, we're getting there. Now I still have to multiply out the remaining two factors. So I have 1/8, 0 to pi. This is going to be 1 plus cosine 2x minus cosine squared 2x minus cosine cubed 2x dx. All right, looks good. Now let's see. Let's go term by term and decide how we would anti-differentiate, okay? Can you take the antiderivative of 1? Yeah, we got it. Could you take the antiderivative of cosine 2x? Absolutely. What about cosine squared 2x? What do you do for even powers of cosine? That's right, you have to use the half angle identity. But since the argument is already a 2x, when you double it, it's going to be 1/2 times 1 plus cosine 4x. Ooh la la. So since already we had a 2x, when you double 2x, it's going to become 4x. Now, last term, what about this cosine cubed 2x? How do you integrate an odd power of cosine? Oh, that's right. That was the first case that we looked at. So remember, we have to make a u-substitution. So you have a few ways you can do that. You can break up the integral. What I like to do is just say, okay, I'm going to evaluate that one off to the side. So aside, I'm going to look at what the integral is from 0 to pi of cosine cubed 2x dx, which remember, I'm going to break it up, pull the odd man out, 0 to pi, cosine squared 2x times cosine of 2x dx. Now remember, I want all of this to get absorbed as du, which means u would need to be sine of 2x, right? And then du is going to be 2 cosine 2x dx. Are we in good shape? No, we're not, because I need that to be in terms of sine instead. So let's go ahead and replace it. I'm going to have 0 to pi, 1 minus sine squared 2x, and then we have cosine 2x dx. All right, great. So now let's go ahead, make our change of variables. So instead of 1 minus sine squared 2x, I'm going to have 1 minus u squared. This cosine 2x dx is equal to a 1/2 du. 1/2 du. And then let's see what our new limits of integration are. So remember, u was sine 2x. So u of the lower limit, 0. U of 0 is sine of 0, which is 0. And then u of the upper limit, pi, u of pi is sine of 2 pi, which is also 0. Well, wait a minute. Since the upper limit and the lower limit are the same, that means the value of this integral is 0. Cool. So then I know this guy right here, this last term, is just 0. All right. Then let's finish up the problem. I think we're ready. So we've got 1/8 integral from 0 to pi. I have 1 plus cosine 2x. Remember, there's this negative here, so don't forget to distribute it. Minus 1/2 x minus, this is going to be, oh, it's just a 1/2, no x. I got excited there. And then minus a 1/2 cosine 4x dx. Okay, before we keep going, I noticed these are like terms, so I can combine them. So we have 1/8 integral 0 to pi, 1/2 plus cosine 2x minus 1/2 cosine 4x dx. And I'm not worrying about the cosine cubed 2x anymore, because remember, I know that's just going to go to 0. So now it's time to anti-differentiate. Antiderivative of 1/2, that's 1/2 x. Antiderivative of cosine 2x, that's plus 1/2 sine 2x. And then antiderivative of negative 1/2 cosine 4x, I got to divide by that 4, so it's negative 1/8 sine 4x. And this all gets evaluated from 0 to pi. And don't forget, oh my goodness, you thought I forgot, didn't you? Almost, there's that 1/8 sitting outside. Okay, so let's plug in those limits. I've got 1/8 times pi halves plus, let's see, sine of 2 pi, that's 0, minus, and then sine of 4 pi, that's also 0, minus, and then now plugging in 0, I'm just going to get 0, 0, 0. All right, so I'm left with pi over 16. All right, and there's your final answer. So as you can see, there's lots of places to make silly mistakes. Just make sure you're methodical, tedious, really detail-oriented, and you have to have your trig down. My goodness, it's essential. Okay, let's look at some more cases now. With sines and cosines, now let's move on to looking at integrals that involve powers of tangent and secant. So our first case, if the exponent m on tangent is odd, what you want to do is break off one of those factors of tangent. So you're going to rewrite it out here, and you're also going to break off one of the factors of secant. Okay, so you had tangent to the m, secant to the n. You take away one from each. This is what you do when tangent has an odd exponent. And then same idea, you want this tangent x, secant x to basically be part of your du. So all of this is going to be your du. Well, then think backwards, okay? What trig function do I take a derivative of and I end up with tangent x, secant x? It's secant. So that means the rest of our integral needs to be all in terms of secant x, which is why now, since we know for sure tangent's exponent is even, you use the identity secant squared x minus 1 to replace it. So everything's all in terms of secant. You make your u sub, and then you can proceed. So that's what you do when the power or the exponent on tangent is odd. Now, other scenario is if the exponent on secant is even. This one's actually a wee bit easier. So if n is even, the exponent on secant, you're actually going to take two of them away. And then secant squared x dx is what you want to get absorbed when you make your change of variables. So that means that you would want to let u equal tangent x. So that means your whole integral needs to be in terms of tangent x. Well, since the power on secant was even, if you take away 2, this is still even, still being raised to an even power. So then you can use your identity that secant squared x equals tangent squared x plus 1. And then you can make your u-substitution and proceed. Okay? Now, sometimes both cases can happen at the same time, meaning the exponent on secant is even and the exponent on tangent is odd. In that case, you could evaluate the integral using either technique, and your answer may not look the same. One might be in terms of tangent, one might be in terms of secant, but using trig identities, you could show that they're equivalent. Okay, so there may be more than one approach and more than one possible answer by appearance, but it's going to be actually equivalent. Here we go. So let's evaluate the integral. We have definite integral from 0 to pi over 4 of secant to the 4th theta times tangent to the 4th theta. So in this case, I only have one technique that I can apply because the exponent on secant is even, and that's it. So I'm going to take away or pluck off 2 of them. So let's rewrite this as integral 0 to pi over 4. Remember, I'm going to take 2 factors of secant away. So now this is just secant squared theta. I still have tangent to the 4th theta. And then here's the other 2, secant squared theta d theta. So that's what happened to my secant to the 4th. That's what you do when the power on secant is even. So here's what you think to yourself. Basically, I want this to be du. or get at least absorbed, right, when we make our u substitution. So you think in your head backwards. Okay, if that's going to be du, then what would I need to let u equal? Well, u would have to be tangent theta. That way du is secant squared theta d theta. All right, fantastic. So if u is tangent theta, my whole integral needs to be in terms of tangent. Let's see here. This is fine. That's going to be u to the fourth. The secant squared theta d theta, that's my du. But wait a minute. I've got this secant squared theta, which I have to change. But good thing we've got that Pythagorean identity up our sleeve. I'm going to replace it with 1 plus tan squared theta. All right, and now we're almost ready to roll. I just got to switch those limits of integration. So lower limit is 0. Let's see what the new lower limit's going to be in terms of u. So u of 0, that's going to be tangent of 0, which is 0. And then u of pi fourths, that's tangent of pi fourths, which is 1. Okay, so now let's switch everything to be in terms of u. So we'll have definite integral from 0 to 1. 1 plus tan squared theta is going to get replaced with 1 plus u squared. Okay, and then remember we have that tangent to the fourth theta. That's just going to be u to the fourth. I'll highlight them so they match. So this tangent to the fourth here is u to the fourth. And then secant squared theta d theta, that's just du. All right, now the rest is smooth sailing. We're just going to distribute the u to the fourth. So we have integral from 0 to 1, u to the fourth plus u to the sixth du. Take the antiderivative, that's 1/5 u to the fifth plus 1/7 u to the seventh. Evaluate this from 0 to 1. And we're going to have 1/5 plus 1/7 minus just 0. And then if I add these two fractions together, I get 12 over 35. And we are done. So not too bad. Okay, there we go. All right, one more example along these lines. We have tangent cubed 2x times secant to the fifth 2x dx. So in this case, the exponent on tangent is odd. And so I'm going to take out one factor of tangent and one factor of secant. Okay, so let's see here. I'm going to be left with, if I take away one of those factors of tangent, a tangent squared 2x. Then I'm going to have a secant to the fourth 2x. And then remember, I still have a tangent 2x, a secant 2x dx. Okay, so when you pluck off one factor like that from tangent and secant, that's because you want this whole expression here to be absorbed or to be du. Okay, so think backwards. If that's going to be du, or get absorbed when we make our change of variables, what does u need to be? Well, u would have to be secant of 2x. You have to keep the argument the same. So just be careful because du, using the chain rule, is going to have a 2 secant 2x tangent 2x dx. Which means secant 2x tan 2x dx is actually 1/2 du. But that's fine. We can add a 1/2 in there. No big deal. It's that secant 2x tan 2x dx that I wanted to get out of there. Okay, beautiful. So now let's be careful here. If u is secant 2x, then that means the rest of my integral needs to all be in terms of powers of secant. So this is fine. This is already secant to the fourth 2x. Oh, but this tangent squared 2x, no, let's switch that out. So I'm going to replace tangent squared 2x with secant squared. You don't need those parentheses. I was just doing it to help separate the argument, but I think we're good. Secant squared 2x minus 1. So we've got this integral. Then secant to the fourth 2x, that's going to be happy as is. And then we've got our tangent 2x, secant 2x dx. Okay, now it's u sub time. So secant squared 2x minus 1, that's going to be u squared minus 1. Secant to the fourth 2x, that's just u to the fourth. And then tangent 2x, secant 2x dx, that's going to be 1/2 du. So here's the du, here's the 1/2. That way it's not bothering us. Put it outside the integral. Get it out of your way. Okay, now let's distribute. So we have 1/2 integral u to the sixth minus u to the fourth du. So this is going to be 1/2. Let's go ahead and anti-differentiate. So this is going to be 1/7 u to the seventh minus 1/5 u to the fifth plus c. I need a plus c this time because it's not a definite integral. And then I have to replace everything so it's all in terms of the original variable. So replace all of the u's with secant 2x. And let's distribute that 1/2 at the same time. So we have 1/14 secant to the seventh of 2x minus 1/10 secant to the fifth of 2x plus c. Very nice. I hope you're especially proud of that one. That was a good one. Okay, now let's look at a few other trig cases. You should already be familiar with the antiderivative of tangent x dx, but we'll just do a little refresher, show you where we come up with it. So remember, we rewrite tangent of x as sine of x over cosine x dx. And then the idea is for this to all get absorbed as du. So u is going to be cosine x, du is negative sine x dx. And then when we make our u substitution, now we have negative integral 1 over u du, right? Okay, and then antiderivative of 1 over u is natural log absolute value of u. So I have negative natural log absolute value. Remember, u was cosine of x plus c. And then snazzy little thing you can do using our logarithm properties, this is negative, but I'm going to move it to the exponent. So this is cosine of x absolute value raised to the negative first power plus c. And we know the reciprocal of cosine of x is secant x. So this is natural log absolute value secant x plus c. And that's preferred typically for a couple reasons. One, it's nice not to have that negative sitting out there. And also we've already seen that tangent and secant have such a nice relationship, right? They've been friends for a long time. We've got a Pythagorean identity with tangents and secants. Their derivatives involve one another. So let's just keep them together, okay? Don't break up the band. Now, cotangent of x dx, that integral is very similar. So you start off by rewriting it as cosine of x over sine of x dx. And then same idea, so you make your u sub. U has to be the denominator, right? So u is sine x, du is going to be cosine x dx, no negative this time. So I'm going to have integral 1 over u du. So this is natural log absolute value of u plus c, and then u was sine x. So you just leave it natural log absolute value sine x plus c. No snazzy trick there. Okay, these ones come up so frequently, and you don't want to waste time doing a u sub that really is so basic. So really you should just memorize these guys if you haven't already, okay? So antiderivative of tangent and antiderivative of cotangent, put these to memory, but you want to at least know where they come from, okay? Very good. Now here's another one that you need to put to memory, integral of secant x dx, because it's going to come up so often, you don't want to have to go through this process every single time. And it's not the most intuitive, let me be honest. So how do you integrate secant of x dx? you multiply by 1, but a very special version of 1. You're going to multiply by secant x plus tan x over secant x plus tan x. Why am I doing that? Because I know this is how to do it, okay? So don't worry, it's typically not something you're just going to sit around and be like, oh, let me just multiply by secant x plus tan x over itself. That sounds like a good idea. All right, then from here, what you do is distribute that secant x in the numerator. Okay, so this distributes. So we're going to have secant squared x plus secant x tan x in the numerator. And then I still have secant x plus tan x dx. And then watch, this is the snazzy little thing that happens. So we're going to let u equal the denominator. So u is going to be secant x plus tangent of x. And then du, let's see. So derivative of secant x, that's secant x tangent of x, plus derivative of tangent of x is secant squared x dx. My goodness, do you see that sitting somewhere in our integral? I do, it's right here. That was convenient. All right, and so from here we have integral. That's going to be du over u. And this is old news, so we have natural log absolute value of u plus c. So this is natural log absolute value secant of x plus tangent of x plus c. Okay. So the reason I say to memorize it is because typically in an integral, in an integration problem, you're not going to just have to find the antiderivative of secant x dx like this, okay? Typically, this is just going to be one part in a bigger problem. So you want to be able to just crank this out really quickly and not have to sit there remembering, oh, what was that sneaky little multiplication trick I had to do so the u sub would work? No, no, no. We have to just put to memory what the integral is, okay? And then use it when appropriate. All right, so let's look at some more examples with secant. It's a tricky little one, that secant. Here's another famous one. So this is integral of secant cubed x dx, okay? Now you might remember we talked about what to do if the power on secant was odd, but in this case I don't have any tangents to work with it. So that case, or the technique for that case, won't apply here since this isn't a product of tangents and secants. We have to do something else. Okay, well, what else do we know? Well, we know about integration by parts. So let me see if I can break this up somehow where by parts would maybe help me out. So this is secant x times secant squared x dx. Do you guys agree? All right, so I can let u equal secant x, and then dv would be secant squared x dx. Why did I pick it that way? Because remember, I have to integrate du times v. And if I had it the other way around, first of all, integral of secant x involves a natural log, and I don't want to have to integrate a natural log sitting there. Doesn't sound good. Also, derivative of secant squared x, I'd have to use a chain rule, so that would make this messy. So that doesn't sound good. Okay. So now I have v, that would be tangent of x, and then du is secant x tan x dx. Okay, so remember we're starting with trying to figure out what the integral of secant cubed x dx is, and that's going to equal uv, so secant x tan x, minus the integral of v du. So that's going to be secant x tangent squared x dx. So this is v du, and this is uv. Okay, now let's look here. What do I do with this secant x tan squared x business? The the power on secant is odd, but you don't even need to go to one of the cases that we had, because remember, I can rewrite tangent squared x as secant squared x minus 1. And watch what slick little thing is going to happen next. So I'm going to just bring this term down here. This is secant x tan x minus, and then now this secant is going to distribute to secant squared x minus 1. So I'm going to have the integral of secant cubed x minus secant x dx. And this is all equal to the integral of secant cubed x dx. Ooh, look at what happened. We have another boomerang integral. So the integral we're trying to find popped back up on the other side. So remember, we can just move it over as if it were a variable all on its own. And so I have integral of secant cubed x dx plus the other integral of secant cubed x dx equals, okay, what's left over on this side? I have secant x tan x. And then be careful, this negative is going to distribute here. So now I have plus the integral of secant x dx. Whew, okay, the worst is over, I promise you. So now these, I can add them together. That's 2 times the integral of secant cubed x dx. This equals secant x tan x plus, oh, that's right, we just went over what the integral of secant x dx is, and we put it to memory, and now we're going to bust it out. It's natural log absolute value secant x plus tan x plus c1. Ooh, why am I doing c1? You'll see in a hot second. Okay, last thing, I need to divide by 2. So we have integral secant cubed x dx equals 1/2 secant x tan x plus 1/2 natural log absolute value secant x plus tan x plus c, and then I'm going to write PS c is equal to c1 over 2. Just so that in our final answer we have a plus c instead of c over 2, right? Doesn't it look so much more classy like this? I'm sure you agree. Okay, so that is how you anti-differentiate secant cubed. You do by parts and then it boomerangs after you do that little trig sub, or I use a trig identity basically. All right, one more. It's relaxing, okay? We're winding down. This is the cool down after the exercise session. So we have integral of tangent squared x plus tangent to the 4th x dx. Now this one might seem strange because we've been dealing with products of trig functions, not the sum of them, right? And I can integrate these separately, but let's see if there's an easier way. How about I factor out a tangent squared? How do you feel about that? So let's take out tangent squared x, and then I have 1 plus tan squared x dx. Oh, and remember, 1 plus tangent squared x is secant squared x. I wonder if that's going to take us places. So here I have integral of tangent squared x times secant squared x dx. My goodness, it sure will, because this secant squared x dx can get all absorbed as du if I let u equal tangent of x. Not tangent squared, because then I would have a nasty chain rule, just tangent of x. Then du is secant squared x dx. And I'm ready to write this integral all in terms of u. So let's see here. So tan squared x, that's going to be u squared. Secant squared x dx, that's du. Very nice. And then now let's go ahead and integrate. So I have 1/3 u cubed plus c. And we are not done because everything was in terms of x to begin with. So I'm going to replace u with tan x. So I have 1/3 tangent cubed x plus c. See, I told you this one would be nice. Okay, so that concludes the lesson. Hope you enjoyed it. Stay tuned. Don't forget to give this video a thumbs up, subscribe if you haven't already, and more integration techniques are on their way.